Today we're going to continue talking about hypothesis testing. So we've established a pretty standard framework for doing hypothesis testing. So we identify the null and alternative hypothesis. From there we can calculate our rejection region and also the test statistic. And then we compare our test statistic to our rejection region to determine whether we want to fail to reject the null hypothesis or we want to reject the null hypothesis and instead conclude the alternative hypothesis. So we're going to be doing the same thing here in section 10.9 of the book, but now we're going to be doing hypothesis tests for population variances. And whereas in the previous sections we'd also discussed how to use the p-value approach for deciding between the two different hypotheses, we're actually only going to use the rejection region approach in this section simply because it gets really complicated with two-tailed p-values for this kind of test, and it's not that important. So we're just going to focus on using the rejection region approach and keep things simple and straightforward. So when you're testing hypotheses about variances, we, as usual, assume that we have a random sample of observations. It's very key that these observations come from a normal distribution. Unlike some of the previous settings where as long as we had a large enough sample size, everything worked out okay, this hypothesis test is actually very dependent on the fact that the data comes from a normal distribution. So this is a really important assumption. So we have a random sample of data from a normal distribution, and the population has unknown mean mu and unknown variance sigma squared. Whereas before, in the previous sections of this chapter, we were interested in statistical inference about the population mean. In this particular section, we're actually interested in inference about the population variance sigma squared. So under the assumption that our null hypothesis, sigma squared, is equal to some value sigma naught squared, assuming that's true, then the statistic chi squared, so this looks like an x squared, but it's actually a chi squared, is equal to n minus 1 s squared divided by the hypothesized value of the variance in the null hypothesis. And that statistic has a chi-square distribution with n minus 1 degrees of freedom. So this actually looks very similar to the formula that we used in chapter 8 to calculate confidence intervals, except that instead of having a quantile down here, we're replacing it with our hypothesized value of the population variance. So we take the sample variance multiplied by n minus 1 divided by the hypothesized variance in the null hypothesis. And as is typical, we can have an upper tail test, a lower tail test, or a two-tail test. Upper tail test is that the population variance is greater than some hypothesized value, sigma naught squared. A lower tail test is that it's less than sigma naught squared. And the two-tail test is that the population variance is not equal to some hypothesized value, sigma naught squared. So we have the test statistic we've already talked about. We'll let little x squared denote the observed, or little chi squared, denote the observed test statistic. And as I mentioned, we're only going to use the rejection region approach to do hypothesis tests in this framework, but it's very straightforward, very similar to what we have seen in previous sections. So for an upper tail test, the rejection region is that our test statistic is greater than the 1 minus alpha quantile of the chi-square distribution with n minus 1 degrees of freedom. So whereas in previous sections we would have a t or a z here, because our test statistic has a chi-square distribution, that's the distribution we need to get our quantile from. So we have that our test statistic is greater than the 1 minus alpha quantile of the chi-square distribution with n minus 1 degrees of freedom. That's the rejection region for the upper tail test. For the lower tail test, we have the opposite situation, where the test statistic is less than the alpha quantile of the chi-square distribution with n minus 1 degrees of freedom. Notice here that we can't simply plug in negative chi-squared alpha. The reason for that is because the chi-square distribution is not symmetric. So whereas the t distributions and the z distributions are both symmetric, and the hypothesis test related to those distributions look very similar, you have to be a little bit more careful and recognize that this is a slightly different setting, so we do things a slightly different way. So for a lower tail test, the rejection region is that the test statistic is less than the alpha quantile of the chi-square distribution with n minus 1 degrees of freedom. And for a two-tail test, we actually have to calculate two different quantiles. We have to calculate the 1 minus alpha over 2 quantile of the chi-square distribution, and also the alpha over 2 quantile of the chi-square distribution. And so we compare whether our test statistic is greater than or less than those critical values, respectively. And so we have to look at these two different quantiles in order to make our statistical decision. Okay, so that's how we do our hypothesis test for a population variance. Let us now do a couple of examples. So a nutritionist claims that the standard deviation of the number of calories in 1 tablespoon of the major brands of pancake syrup is 60. She took a sample of 18 major brands and calculated the number of calories for each brand. The sample standard deviation for the number of calories was 67.8, and our question is there enough evidence to reject the claim of the nutritionist at a significance level of 0.1? And we're going to assume that all the appropriate assumptions are made. So why don't you pause this video and work on this on yourself for a few minutes, see if you can't solve the problem on your own, and then unpause it and we will go over the solution together. Okay, so the first thing that we want to do is state our null and alternative hypotheses. And in this problem, the null hypothesis is that the population standard deviation is equal to 60 versus the alternative that it is not equal to 60. You might be confused and be saying to yourself, wait a second, I thought we were doing a hypothesis test about the population variances. And that is true, that's the one that we learned. So this is equivalent to saying that the population variance is equal to the population variance is equal to 60 squared versus the alternative that the population variance is not equal to 60 squared. So these two hypotheses are really equivalent, though our test is going to be in terms of the sample variances and so on. So let's determine our rejection region. This is a two-tailed test, as I'm sure you all noted, and so we need to compare our test statistic to the alpha quantile of the chi-square distribution. So that is 0.9 here, oops, 0.95. So we're comparing our test statistic to the alpha over 2 quantile of the chi-square distribution, which here is denoted as chi-squared of 0.95, or the other situation where we reject the null hypothesis is when the test statistic is greater than the 1 minus alpha over 2 quantile of the chi-square distribution, which is going to be chi-squared of 0.05 in this case. And if we look up those values in R, we're going to find them to be equal to 8.67 for the alpha over 2 quantile, and for the 1 minus alpha over 2 quantile, it's going to be 27.59. Okay, and the way that we get these commands is just using Q chi-squared. We put in the correct quantile, and then degrees of freedom is equal to 17 in this case. And so just so you can see those values in R, okay, I've calculated them right here. So the alpha over 2 quantile, which is the 0.05 quantile in this case, is equal to 8.67, and the 1 minus alpha over 2 quantile, which is the 0.95 quantile, is 27.59. Okay, so we have those two different quantiles that make up our rejection region. And our test statistic is simply going to be the number of observations minus 1 multiplied by the sample variance divided by the hypothesized variance, 60 squared, which equals 21.71. And comparing our test statistic to our rejection region, it's pretty clear that this test statistic does not fall in the rejection region, so we fail to reject the null hypothesis. So we might say something like, there is insufficient evidence to conclude that the standard deviation of the number of calories in 1 tablespoon of the major brands of pancake syrup is different than 60. So quite a mouthful, right, since we're talking about pancakes there. There is insufficient evidence to conclude that the standard deviation for the major brands of pancake syrup the standard deviation of the number of calories in 1 tablespoon of the major brands of pancake syrup And of course, we cannot conclude that it's different than 60. So all that's really saying is that there's insufficient evidence to reject the null hypothesis. There's insufficient evidence to reject the null hypothesis. There's insufficient evidence to conclude the alternative hypothesis. So we've stated in terms of the alternative hypothesis. So we cannot conclude that essentially the standard deviation of our population is different than 60. So kind of a silly little example, but at least it gives us some practice in doing that kind of hypothesis test. And let's just do one more for good measure. So test the claim that the standard deviation for the number of aircraft stolen each year in the United States is less than 15 if a sample of 12 years had a standard deviation of 13.6. Use a significance level of 0.1, and we'll assume that we do in fact have a random sample from a normally distributed population. So the assumptions of this hypothesis test are met. So once again, why don't you pause this video briefly and then see if you can't answer this question on your own, and then we'll come back together in a few minutes and solve or look at the answer together. Alright, well I hope you were successful in answering that question. Let's look at solving this problem together. So firstly, we state our null and alternative hypotheses. So in this case, the alternative hypothesis is that the standard deviation for the number of aircraft stolen is less than 15. The null hypothesis is that it's equal to 15. So similar to the previous problem, this is the same thing as saying that the null hypothesis is that the population variance is equal to 15 squared, and the alternative is that the population variance is less than 15 squared. So let's calculate our rejection region, which is a little simpler this time since we have a lower tail test, only a one-sided test, and it's going to be when our test statistic is less than the the alpha quantile of the chi-square distribution. In this case, our chi-square distribution is going to have 11 degrees of freedom, 12 minus 1, and so when we look that up in R, we want to reject the null hypothesis when our test statistic is less than 5.58. And so what we do, just looking in R here, is we want the 0.1 quantile of the chi-square distribution with 11 degrees of freedom, which as you see here is 5.58. So that's where we get the number for our rejection region. Now let's calculate our test statistic. So our test statistic is going to be 12 minus 1, or 11, multiplied by the sample variance, divided by the hypothesized variance, which is 15 squared. When we calculate that out, we get 9.043. And once again, similar to the previous problem, the test statistic is not in the rejection region, so we're going to fail to reject the null hypothesis. So we would say there's insufficient evidence to conclude that the number of aircraft stolen each year in the US has a standard deviation less than 15. So that's really just a fancy way of saying that there's insufficient evidence to conclude the alternative hypothesis. So we cannot conclude that the standard deviation of the number of aircraft stolen each year in the US is less than 15. So there we have two examples of how to perform a hypothesis test for a population variance. Tying this back to the previous situations, we always state our null and alternative hypothesis, we determine our rejection region, we calculate our test statistic, and then obviously compare that to the rejection region, and depending on what our statistical decision is, we conclude our results in the context of the problem. So essentially we explain our results so that someone who's not familiar with statistics has a reasonable chance of understanding them. So on Tuesday, we will continue on by talking about regression analysis. But I hope that you guys had a fantastic weekend, and I will see you guys on Tuesday.